Dominic just had a sudden cardiac arrest. Hillary was in the next room and came to see what the large thud was. As she arrived in the room, 5 seconds had already elapsed. Hillary's been trained. She determines that Dominic is non-responsive. She rolls him onto his back and she checks to see if he's breathing normally. He is not. She pulls out her cell phone and dials 911. 35 seconds is gone. She tells the operator where she is, what is wrong, and what she's doing about it. She begins chest compressions about 48 seconds after the arrest, a lot more promptly than happens most of the time. But Dominic's probably not going to make it. Hillary weighs 115 pounds, and she has to push the chest with 110 to 125 pounds to get 2-inch compressions. And most people can't continue manual compressions until 911 arrives. But this is what we've taught year after year after year. There is a better way. Let's take an integrated look at bystander CPR endurance and 911 response time. This graph shows the probability over time that the ambulance crew will not yet be hands-on at the victim. The starting point of this graph on the left is the time of the cardiac arrest. The space between the dots is 1 minute. The response time data was generated by reviewing a year's worth of actual data and adjusting it for factors that consume time between the time of the arrest and the time the ambulance gets the call to respond, as well as for the difference between when the ambulance reports on location and the time the crew actually has their hands on the victim. These data include only the 95% of the actual data closest to the average. 1 in 40 ambulance runs for a cardiac arrest will generate shorter times than the 3.8 minutes minimum, and 1 in 40 will generate longer times than the 17.4 minutes maximum. This 95% sample is called the 2 sigma data, or 2 standard deviation data. Using 2 sigma data permits us to more clearly see the core problems without getting distracted by response time that was accidentally fast because, for example, the ambulance happened to be in front of the victim's home when the call came in, and so forth. The source of the endurance data is a study Slick performed in August and September of 2012. Slick studied the CPR stamina about 4 dozen people, first while performing manual chest compressions and then using the heel of the foot to compress the chest. This second technique is called pedal chest compression. The people we tested were selected to form a cohort whose age distribution approximately matched the probability of having a cardiac arrest at that age. We took this approach under the assumption that in the lone rescuer case, the other adult was likely to be approximately the same age as the victim. We grouped the volunteers into 6 decades, 40s through 90s, and it was the total in each decade that we tried to get to match the probability distribution of a cardiac arrest when one was in one's 40s, one's 50s, and so on. This graph highlights the challenge faced by the bystander. At an absolute minimum, the bystander will have to perform guideline-compliant chest compressions, GC3s for short, for at least 3.8 minutes, but more likely for 9.7 minutes and perhaps as long as 17.4 minutes. The numbers at each red arrow tell the tale, a tale that becomes quite alarming when one considers that more than 2/3 of all out-of-hospital sudden cardiac arrests occur in the home, and 1/3 of all homes are 2 adult homes. Performing CPR the way it is commonly taught means that 1 in 4 lone rescuers will be able to perform GC3s until the fastest expected arrival of the ambulance crew at the victim's side. Fewer than 1 in 5 will be able to perform GC3s until the average response time, and none will be able to perform GC3s until the maximum response time. However, when performing pedal compressions, 3 times as many will be performing GC3s at the minimum response time, 4 times more at the average response time, and that multiplier keeps on growing as each minute passes. In preparing for this study, we found that pedal compressions were investigated several times, beginning in 1978. One of the researchers found that there were fewer misplaced compressions with the pedal method, but the technique didn't offer any compelling advantage because compression depth guideline at that time was half that of today. The amount of force required to compress a chest 1 inch is far less than half that required to compress it 2 inches. Slick's recommendation is that when you need to perform CPR, perform the chest compressions manually unless 1, you cannot get down on the floor, or 2, arthritis prevents you from pressing on the chest forcefully enough, or 3, you have become too tired to perform GC3s, or 4, the chest you are compressing is too stiff for you to compress using manual compressions. Under these preventing conditions, you should consider an alternative method such as pedal compressions. Some people are initially surprised that the compression method can be dictated by chest stiffness. Because 20% of your body weight approximately is below the hip joint, when you rock from the hips to perform manual compressions, only about 80% of your weight is available for chest compressions. If you switch to pedal compressions, your entire body weight is available. You can get about 25% more force into a chest compression using pedal compressions than using manual ones. And you should be aware that a human chest requires anywhere from 40 to 180 pounds to compress 2 inches. By way of an example, I apparently have a chest that requires 130 pounds to compress 2 inches. I measured the force required to compress it half an inch and used chest stiffness data to extrapolate to the force required to compress my chest a full 2 inches. My wife weighs 115 pounds. When performing manual compression, she can apply a maximum of 92 pounds to my chest. That's why I have urged her to use pedal compressions if she is treating me for cardiac arrest. That is also why I gave her a backpack full of rocks for Christmas. The backpack weighs about 20 pounds, and that should be more than enough to permit her to perform GC3s on my chest. Seriously, Slick is currently preparing to test weighted vests with underweight rescuers. So where does this leave us? Or more specifically, where does this leave you? Each of us has more than a 10% chance, at least once in our lifetime, of seeing a loved one, a family member, a friend, a coworker, or so forth, die of a cardiac arrest right in front of our eyes. And these people have the same odds of seeing someone go down as you do, and you might be the person they see go down. Well, first, there are 3 possible outcomes from a cardiac arrest. First, you can stay dead. Second, you could be brought back with minor or no neurological impairment, provided the GC3s are performed from the time of the arrest until the victim is resuscitated. Or third, you could be brought back, but with enough neurological damage that you can't manage the activities of daily living without assistance. For obvious reasons, people in this third category, also includes comatose and brain-dead people, are not counted as being survivors. The one thing most people in this terrible third category have in common is the lack of immediate CPR that continued until the ambulance crew took over. That's what the big deal is about bystander CPR. So what I'm suggesting you consider is really simple. Number 1, make a list of the people most likely to be near you if you have a sudden cardiac arrest. Number 2, make sure everybody on that list not only knows how to perform CPR, but also knows how to get you out of that recliner chair or out of the bed onto your back on a hard, flat surface like the floor, because you can't perform adequate chest compressions on someone lying in bed or seated in a recliner. That's why the gurneys in an emergency room are so uncomfortable. And number 3, if some of the people on that list weigh less than 140 pounds, keep a backpack with 30 pounds of rocks in it in your home. That's the most likely place where you will suffer your cardiac arrest. One last point. When performing pedal chest compressions, stand at the top of the victim's head with the toes of the inactive foot by the ear. Place the heel of the active foot at the CPR point, a point where a line down the center of the chest crosses a line between the nipples. Keeping the inactive foot back at the ear forces the toes of the active foot into the air and helps prevent you from applying force to the bottom of the breastbone. And this is very important.